16.4 is on Green's theorem, and this is specifically in 2D. So we will extend this to 3D in the future sections. So Green's theorem, we need a couple definitions first before we continue. Just lining things up here. So first we want to define a simple curve. Okay, so a curve, so here's a definition. Excuse me. Okay, a curve C given by R of t equal to x of ti plus y of tj for t in a b, the closed interval from a to b, is simple if it does not cross itself. If it does not cross itself. Okay, so one thing, this isn't really part of the Calc 3 stuff, but how would you define that? How do you define something that doesn't cross itself? It's worth talking about on an interval. So we'll say that is, i.e., R of C does not equal R of D for all C, D in A, B. So that's one way to describe it. So these are arbitrary values inside the interval, and for every single arbitrary value, you never have equality, which means they wouldn't, cross. So here's some cases. So here's one case. So that curve would be simple, but not closed. Then you can have a closed curve, kind of whatever like that. Okay, that is simple and closed. And then you could have something like this, typical figure 8, that is not simple, but it is closed. So it crosses itself, obviously, right there where it does that. Okay, so we are going to be interested in a simple closed curve, by the way. That's what we'll be looking for. Okay, let us continue. Okay, so next definition. A plane region R is simply connected is the next thing. So a plane region R is simply connected if its boundary consists of one simple closed curve. If its boundary consists of one simple closed curve. So like the middle one above is really the one we're interested in. And so they'll look like this. We want a region, something like that. This is simply connected. Oops, get rid of that thing. And I'm having to move everything over for some reason the way I'm writing. I don't know what it is. Okay, sand, we'll talk about this later, but we have it oriented in a certain direction, like as a particle goes around it. So this is our region R, and it's simply connected. Okay, and then let me go ahead and highlight that. So this is our region of interest, all in here. Okay, so that's region in question. Then you could have something like this. Oops. And then it's oriented, it'll be counterclockwise like that. But then you could have it broken up into regions like this inside. I'm going to zoom in a little bit. So this could be our region R, and then this is our, so this is not what we want because this is multiple simple closed curves. Okay, but it gives you an idea what we're looking for. So there's another one. So this is not simply connected. Because remember, it has to be one simple closed curve. This boundary is defined by multiple simple closed curves. Although they don't cross itself, right? So that's the other thing. And then you could have, of course, the thing above where it crosses itself. So this one would be not simple. As well, not simply connected as well because it crosses itself. But it is one curve. So you see the differences on what could happen. Okay, so we want the simple, the general case on the right. That's the one we're looking for. So this is your region R. Also, everything in green there is your region in question, but we want the one on the left. Now you may define it, and I believe our book does. You can define it, these theorems, in terms of other cases, but what you're really doing is just applying the first case multiple times, and we're going to just not deal with that right now, basically. All right, let's continue. I think next we are on Green's theorem. Okay, so actual definition. Green's theorem says we want our region R, let R be a simply connected region with a piecewise smooth boundary C. Piecewise smooth boundary C, oriented counterclockwise. Like I drew it above. So I was going counterclockwise. If M and N have continuous first partials, so if M and N have continuous first partials, in an open region containing R, then so the open region part really isn't a big deal. It's just essentially putting a bigger region around your simply connected region. So the key is that the boundary is simply connected and it's piecewise smooth. So it could like a circle, then a line, that kind of thing. All right, then you get this formula, which is kind of nice, kind of cool. So you picture the region above as your C. So that's your C. And so you have a simple closed curve over C, and it's M dx plus N dy. You basically integrate over that with a double integral over the region. So the curve C is defining the region R. So you're going double integral over R. And then what you do is you do the partials. Partial N respect to X minus partial M respect to Y. dA. So you're converting this line integral to this double integral over a region. Now, if F equal to Mi plus Nj is conservative, well, we know it's closed anyway, and you will get 0. But that'll show up real easily here, because to check to conservative vector field, this is what you do. You check to see if partial nx, partial my are equal. Well, then you'll get, if they're equal, you get 0 right there when you subtract them. So it kind of all comes together. But what this specifically does is allow us to not do a line integral, and we can do a double integral over a region. And often, not all the time obviously, but often when you do derivatives or partials, it simplifies the expression, the function. So that's the idea. So you need to picture too a simple closed region like this, oriented counterclockwise, and that's just kind of how it will show up. But so you have that as your region like this. Okay, so there's your R, and you could have it, start and stop like this. Let me show you just a little something or other. So it could go like this, and then have a corner or something, and then go straight maybe for a little bit, and then go back. Who knows? It's kind of a weird thing in there, but whatever. I mean, it could do something weird like that. Okay, so there's your region. But you are also picturing flux going through that. So your flux would be passing through. So you always have to consider this stuff not just by itself as an integral, but that when I say flux, I actually haven't defined that yet. Sorry. I mean the vector field. The vector field's passing through it. We will define flux here shortly, but vector field F is passing through that thing. Okay, and then that's acting on it, and so there's more to it than just the integration. You have that vector field acting on it. Okay, let's go ahead and do an example. Next. Okay, so we'll do one example. There's plenty to look at in the book and stuff. So, okay, evaluate the line integral over c of 4 plus e to the root x dx plus sine y plus 3x squared dy, where c is given by this, and this would have been stated or drawn. C is the sector in the first quadrant. So you have, and I'm going to do it like this and put it up there as a circle. So we're going to just erase, just make that a bigger circle. So not that big. Okay, so C would be like that. And then let's make that smaller. And it's from A to B. So we're going to erase the rest of these. And it's just in the first quadrant. Like that. And we'll go, this is A to B, A to B, and you keep those in there as AB, so there's nothing specific. So it's oriented counterclockwise, so it would be like this. You can see that it's piecewise continuous because you have the edges there. That's our region R. Okay, so right now we're thinking maybe we do polar, just saying. Depends on what the evaluation looks like. Okay, so there's R. Okay, so that would be given. All right, so we have, this is M, this is N. It's always M, N. Now you need to state the hypothesis. So this is the key piece to these theorems. When we get to all these theorems, is you need to state the hypothesis, even if you don't necessarily have to show it, but you have to at least state it. Let R be simply connected region. Okay, that's fine. M and N have continuous first partials, so you'd have to state that. Okay, so right here, by observation, basically, R is a simply connected region defined by a piecewise smooth curve C. So again, you have to just say it. What else? M and N, and I wrote them underneath there so you'd know what they are. M and N, or you can just write them out. Have continuous first partials. Have continuous first partials. Therefore, we may apply Green's theorem. So let me come back over here as if I'm stating this. Therefore, we may apply Green's theorem. And so we can, just go back to Green's theorem, instead of doing this line integral, which basically, they kind of suck often. I don't like them. We can do a double integral and do those partials, which should simplify this a bit. All right, so we're going to apply this. Oops. We're going to apply this instead. So we can calculate those partials and evaluate over the region. Okay, we'll talk about that in a second, but partial in x would be 0 and just 6x minus partial my is just 0, and that's dA. All right, so you just have double integral over that region. So what are we going to do next? Think about it. We're going to change to what? We want to change to polar. And by changing to polar, this will simplify this thing quite a bit. Well, not simplify a lot, but it'll definitely make it better. So yeah, we change the polar, and then we can do these representative sectors like this, right, from there to there. So we're doing all this stuff here. 0 to pi halves. We're all good to go. So yeah, we're going to do all that. Okay. So, and then x will just be cosine theta, right? So we will say this is equal to, bring out the 6, and then it's the double integral. And then we're going to say r goes from a to b, and theta, as you sweep, right? So theta goes from 0 to pi halves. So 0 to pi halves. And you have r cosine theta is x. And then what? You have to say r dr d theta. So going right back to chapter 15, just like that. Okay. Equal to 6 times the integral from 0 to pi halves, integral a to b, and that's r squared cosine theta dr d theta. And it doesn't matter the order in this case because they're independent. So work that out. For r, you'll get what, 1/3 r cubed. Subtract, and then for cosine, you're going to get sine, and then it's just 0 to pi halves. So I'll let you do the calculation. But what you get is 2b cubed minus a cubed. Okay, so check that. Okay, let's try this one. So next one, evaluate. The line integral over c x squared plus y cubed dx plus 3x y squared dy where C is given by this. And again, this would have been either drawn up or described more carefully. So you go over 1, 2. We're going to go like this. And then this is parabola. And so it's oriented like this. And so you have y equals x squared. This point is 2, 4, and I'm just kind of freehanding it right now. This value is 2. Okay, so there's my region that in question. Okay, so this is my region. It's a simple closed curve defined by those boundaries, and that's what matters. Okay, and this goes pretty quick because watch, you have, this is your M, this is your N, and again, before you apply the theorem, you must state that the situation, the question, satisfies the theorem. So, the hypothesis of the theorem. So you would say M and N have continuous first partials. Specifically on R2, so on the plane. R, the region R, is defined by a piecewise smooth simple closed curve. Defined by and I'll just speed this one up. We're almost to half an hour worth of video here. All right, so okay, so that's true. And you know, if this is like a test, you just write it out, of course, but okay, R is simply connected. That would probably suffice, really. Just say that. So, therefore, we may apply Green's theorem. All right, so then you have this is equal to the double integral over R, partial n respect to x minus partial m respect to y, dA. Well, when you do that, what do you get? Partial n x is 3y squared minus partial my is 3y squared dA. And do you see what you get? You get the double integral over R of 0 dA, which of course is 0. Wow. Okay, so that's what you want to have happen. That's what makes it easy. You could have shown, that these are the vector field that defines that, or these values, the M, the F, N, Mi plus Nj is conservative, all that, but you can just essentially just evaluate it and you'll get 0, which is really the same thing. Okay, so that could happen too. Okay, next on to parametric surfaces.